Continuing on here with section 3.7, Absolute Value Equations and Inequalities. Our learning target for today and what we're shooting for is I can solve inequalities involving absolute value. Big ideas for this section. An equivalent pair of linear equations or inequalities can be used to represent absolute value equations or inequalities. Absolute value equations and inequalities can be solved by first isolating the absolute value expression, if necessary, then writing an equivalent pair of linear equations or inequalities. We can write absolute value inequalities as compound inequalities. The graphs on the top of page 209 show two absolute value inequalities. So here we have the absolute value of n minus 1 is less than 2. Remember, absolute value, guys, represents our distance. So we want that distance away from n to be less than 2. And we show that from our middle point here, less than 2 goes from the middle 2 away in each direction, but it's touching it. It goes towards that middle. We want that distance to be less than 0. It could be 0.1, it could be 1.1, it could be 1.9, it could be 2, just about 2 anyway. We keep that open circle. But same idea, we want that distance to be less than 2 away from our middle. The second one is our absolute value of n minus 1 is greater than 2. Remember, absolute value represents a distance, so we want our distance away from that middle to be more than 2. So our middle here is at 1 if we were to solve this here, and all of our shaded in is further away than 2 units from that middle. This brings us to our take note on page 209, solving absolute value inequalities. To solve an inequality where the absolute value is less than a value, solve a compound and inequality. To solve an inequality where the absolute value is greater than a value, solve a compound or inequality. It's not perfect by any stretch of the imagination, guys, but here's what I usually do to remember. It's a little bit like less than, which I know is a bit of a stretch, and great or, which again I know is a little bit a bit of a stretch, but that's how I remember. So if our absolute value is less than a value, it's an and inequality. If our absolute value is greater than a value, it's an or inequality. And again, if we look at those graphs, that's what we're getting at. If it's less than, if our distance is less than, it means it's less than in both directions. It's only the things in between our value and its opposite. If it's a greater than, it's further away than that value in both directions. So it's further away in the positives and on the negative side. Example 4 here is solving a greater than or equal to absolute value inequality. What are the solutions of the absolute value of 8n is greater than or equal to 24? Then graph the solutions. So we solve these very similarly to how we solved the equations. Once our absolute value is completely by itself, means the only thing on the left side or the right side, we take whatever's inside the 8n with our value exactly as it's written, and we take whatever's inside with the opposite. And we know that whenever we change the sign on an inequality, guys, we also have to flip there. It's like we multiplied this by a negative 1. And anytime we multiply or divide by a negative, we have to flip that inequality. Every single time when we solve absolute values, guys, inequalities, we're going to have one greater than and one less than. Whether it's an and or an or, that does not matter. This one, remember, greater means it's going to be an or. We want that distance to be further away. And if you're not sure, guys, solve it first, graph it, and then go from there. Okay? The or and the and are very, very important in these because otherwise we don't really know what we're doing with those values. So from here, I divide by 8, n greater than or equal to 3, divide by 8, n less than or equal to negative 3. To graph this, I have negative 3 is in between negative 4 and -2. I have 0 in the middle, and I have 3 is in between 2 and 4. I put a circle at 3. I fill it in because of that little equal to line underneath my absolute value, because it's, with my inequality. And I want numbers that are greater. We match our inequality with our arrow. Then, at -3, it's equal to, with my inequality, so less than or equal to, so I fill in that circle. Since my variable's first, I match my inequality with my arrow, and I shade this way. This is an OR because there's a gap in the middle, and because I graph both exactly as they're written. So here's my solutions. Here's my graph. I want my distance to be greater than or equal to 3 units away. So from 0, I'm more than 3 away. I'm more than 3 away. Go ahead and pause and try here if you'd like. Okay, because our absolute value is completely by itself, it's the only thing on that side of the inequality. We take whatever's inside, exactly as it's written, with the greater than or equal to 5, and we take whatever's inside with the opposite. But with inequalities, remember, if we flip the sign, we have to flip our inequality. It's like we multiplied by a negative, which means we change the inequality as well. Because I start off with a greater, it's an OR here. Solve, subtract 4. Whatever I do to one side, I do to the other. Divide by 2. X greater than or equal to 1/2, or x is less than or equal to -9/2, which is -4.5. Now we graph it. 0, 1, half is right between them. -9/2, or -4.5, is between -4 and -5. I put a circle at 1/2, fill it in because it's equal to, and because my variable's first, I match my inequality with my arrow. I want numbers greater than 1/2, like 1. -9/2, I put a circle, I fill it in because of the equal here, and the less than matches my arrow. Because there's a gap in the middle, it's an OR. It's also an OR because it's a greater. We want that distance to be further away from our center. Okay. ORs go out, grators go out. There's bigger distance in between them. Example 5, solving a less than or equal to absolute value inequality. A company makes boxes of crackers that should weigh 213 grams. A quality control inspector randomly selects boxes to weigh. Any box that varies from the weight by more than 5 grams is sent back. What is the range of allowable weights for a box of crackers? So, first step here, word problem, don't panic. Okay, we can figure out what we're looking for. So, the weight that we want is 213. And it can't vary by more than 5 grams. So it has to be within 5 grams of that. So our actual weight and this have to have a difference, so the change between them, that is less than or equal to 5 grams. It can be up to 5, but anything more than that doesn't work. Guys, this deals a little bit with like tolerance. Okay, when you get something that says it has a certain weight or a certain length, there's a little bit of error that's allowed. So it could be a tiny bit more, tiny bit less, and companies, when they're manufacturing things, determine what that tolerance is, how far away it can be but still be accepted. And that's what we're getting at here. So the amount that we measure, our weight, minus the original. This is the difference, guys. And we put that in absolute values because we want that difference whether it's more or less. It doesn't matter. But it can't be more than 5, which means it has to be less than or equal to 5 grams. Okay, the difference in our actual weight and what we want it to weigh, 213, whether that's positive or negative, it doesn't matter, so we put it in an absolute value. It's got to be less than or equal to 5. Okay, so to solve this, to find that allowable range, again, as long as the only thing we have on this side of our inequality is absolute value, we take whatever's inside with how it's written, less than or equal to 5, and we take whatever's inside greater than or equal to negative 5. Again, we flip that inequality anytime we change the sign on the number. It's like we multiplied by a negative. Add 213. So W is greater than or equal to 208 grams. W is less than or equal to 218 grams. This is an and because there are things that are less than 218 and more than 208. This is an and. If we wanted to, guys, remember that with ands, we can write them as one inequality. W is less than or equal to 218. And remember, we're eating W, so we keep eating W. We're pointing at 208, point at 208. Okay. Another way to do this one, guys, is from the get-go, since we see a less than there, we can put a less than or equal to negative 5 and do it as one inequality. That only works with ands. So just be careful there. Go ahead, pause, give this a try. Food manufacturer makes 32 ounces boxes of pasta. Not every box weighs exactly 32 ounces. The allowable difference from the ideal weight is at most 0.05 ounces. Write and solve an absolute value inequality to find the range of the allowable weights. So again, we take our actual weight minus our goal, which is 32 ounces, less than or equal to, because it can be at most 0.05. This is an and, so if we wanted to, we could write it as one inequality with a less than or equal to negative 0.05 here too. Or we can split it into two pieces. W minus 32, less than or equal to 0.05, and remember less than W minus 32. To change it to negative, we have to flip our inequality. Add 32. W is less than or equal to 32.05, and W is greater than or equal to 31.95. You can write that as one inequality if you want to, because it's an and, like this, and these are ounces. Real quick recap, an equivalent pair of linear equations or inequalities can be used to represent absolute value equations or inequalities. And absolute value equations and inequalities can be solved by first isolating the absolute value expression, if necessary, then writing an equivalent pair of linear equations or inequalities. And there is your assignment.